Hello everyone and welcome to this video. I'll be providing explanation of correlation and then explain how we can use R as the tool to test correlation between two variables or in statistical terms conduct a bivariate correlation test. Let's give a simple example. Have you ever taught or asked or been asked the relationship between, let's say, um, someone having more education and having more kids, or let's say someone having more years of age and having done more number of travels? If yes, then in a way you're thinking about a problem that has a implication of correlationships. So there's a difference between correlations and causation. A correlation relationship is a type of relationship where one variable does not cause the other variable to change. It's rather a, a coexistence of two relationships whose changes are reflected on each other. Let's say if somebody has more years of education and more number of children, does that mean having more children, having more years of education causes having more children? No, but they're correlated. Maybe they're factored, or maybe they have other uh, variables or co-variables or confounding variables or cofactors that contribute to that relationship, but one does not necessarily affect the other. Or let's say someone being having more age in years and having done more travels. Does that mean if you get older it causes you to travel? Not necessarily. Rather, there are other reasons that can actually contribute to this correlationship. Let's say the older you are, let's say the more savings you will have, or the more opportunities you will have to travel. Let's just talk about the two types of correlationships, which are positive and negative correlation. So a positive correlation is when when the trend in one variable is correlated with the same trend in the other variable. In other words, let's say if we gather a statistical data of uh, a number of people about their age and the number of travels they have done, let's say we find out that, you know, someone who was 20 years old, 10 years old have only traveled, let's say, two times, so two will fall here. This is the y variable, this is x variable. So let's just plot their number of travels based on their age on this scatter plot. Let's say we find someone who's 10 years old but have only traveled, let's say, seven times. Let's say we find someone who's 15 years old who've traveled, let's say, 10 times. Let's say we find someone who's 50 years old and have traveled 40 times. So that will be something here. Let's say we found someone who's 30 years old but have only traveled 20 times. So we find someone who was 35 years old have traveled 27 times, or such. This actually shows a positive correlation. A positive correlationship is the when when one when an increase in variable x in, reflects the same trend in variable y. So as you can see, that as the age goes high, as the age goes high, then the trend of travel goes high. So this is actually a positive relationship. And so a negative relationship is vice versa. Let's say uh, we find through the survey that, let's say, someone who was 70, 60 years old have only traveled five times. The person who was 70 years old have only traveled one time. Or so let's say somebody who was 60 years, 58 years old only traveled zero times. I mean, like not like one time maybe. Let's say somebody who was 20 years old traveled 15 times. Let's say somebody who was 12 years old or is 30 years old traveled 25 times. So let's say someone who's 35 years old traveled um, 35 times. There you go, or such as such. So this actually shows that this is a negative correlation. In other words, the decrease in one variable causes decrease in another variable. So as this decreases, sorry, the decrease in one variable or increase in one variable causes the vice versa on the other variable. So as this decreases, this increases. So as the age decreases, as the age goes down, the higher the travel goes. So if somebody has less years of age, they have higher number of travels. So this is called negative correlation. So I'm hoping that before we go to R and provide explanation of how to use R for the analysis, I would like to make sure that it's clear what a positive correlation, what the concept of correlationship is and how it actually differs or how it's different from causation and what positive and negative correlationships are. And it's very important to understand that correlationship is not causation. So let's go to R. Um, all the example and the case studies will be in R. I'll be moving back to a Word file where I will explain the coefficient of the coefficient and how they're interpreted. But pretty much everything will be on R. So today I'll be studying the correlationship between the followings. Uh, so I selected um, this simple data set from the Harvard University economics page, econometrics page. A simple data set from the years of we really don't know what years they are, but pretty much there are 12 variables here that each explains a indicator of socioeconomic uh, related uh, subject in a country that we don't know. So what I did is I exported this as an Excel format as an SPSS. I exported into SPSS as an .sav file, and I'll be importing it onto R for analysis. But for right now, just remember that there are 12 variables, and each variable as economic indicators. So let's go to R now. We will be studying years of education and earning. So we will be studying years of education and earning. So that will be where years of education. That will be this one, variable 3, and earnings will be variable 9. So we'll be looking at multiple variables here for correlation analysis today. I have three examples because the first example to illustrate what a positive correlationship is. The second one is to show what a negative correlationship is, and the third one to show how non-existent of correlationship in a data means and how the test can actually validate that. So positive correlation, negative correlation, no correlation. So the question is there any correlation if yes, are they significant? Well, to begin with, in order to import a SPSS file or a file with .sav extension, you will need to install the package foreign, which I already did. I don't want to want R to I don't want R to take more time by installing. So make sure you activate the foreign library, and once activated, you can go ahead and import it on. I select core data. That will be the name of the variable on R. So we have the data set now. All the variables are there. Um, make sure to attach them so that you don't have to, as I explained in a separate video, you don't have to use the dollar sign every time you want to call in a field from a variable. So if you attach it, you don't have to use the variable name each time you call in a field. So now the variable is attached. There are some assumptions about this test is that each of these samples are randomly selected so that there's no bias in them. And then they're parametric. Remember that, you know, for Pearson's correlation, the one that we are doing today, the data has to be parametric. It has to be if it's and it has to be normal. If it's not normal and not parametric, then there are other types of tests that we will use, and I explain it below here. And so to begin with, let's just plot um, both of the variables. Like I said, we are testing the relationship between years of education and earning. Is there a relationship between the numbers of years in education and earning? Let's check it. So, bingo, we have the plot here. As you can see, each of one of these plots actually plot attributes explains uh, each of these numbers from the data set. For example, and these are in dollars, as explained on the variable data dictionary. Let's say, for example, this person has all around 10,000 earnings yearly, and then he or she has around maybe 4 years or 3 or 4 years of education. Let's say somebody over here who has around 25,000 yearly income and has an experience of almost 17 years. So as we can see from this chart, this is actually a positively correlated relationship. It means when one variable goes high, the other variable goes high. So the trend coexists linearly in both of the variables. So it's a good practice that before we test the relationship through a statistical tests, we should plot it to actually look at the actual chart to see if we can visualize any relationship through the scatter plot. And once we designate that, and also we can run some tests for assumptions for normality, which I've already done, and these are normal data. I don't want to do it again here, not to waste time of this for this video. Once we did the plot, we can go ahead and run the test. So remember, this is going to be a Pearson test. There are three correlation tests: Pearson, Spearman, and Kendall-Tau. So Pearson is used for parametric and normally distributed data. But for other for example, rank based data, or for non-normal data, depending on the type of data, there are other two options that we can use. One of them is Spearman, and the other one is Kendall. I'll have separate videos on those. But since our distribution is normal, we can go ahead and use Pearson's correlation. So we run it, and it gives us an indicator, coefficient of 0.46. So how do you interpret this? Let's go to this matrix that I that I wrote here. So the correlation coefficient is if we get a result of 1, then that means a perfect positive correlation. In other words, if somebody gets 2 in one variable, then the other variable should be 2, 2. That means a perfect positive correlation. And if there's anything between 0.90 to up to 0.99, uh, as it's a very strong correlation. If 0.70 to 0.90, it's a highly strong positive correlation. 0.50 to 0.70 is medium positive correlation. 0.30 to 0.50, weak positive correlation. And if it's 0.01 to 0.30, it's negligible positive correlation. And if it's 0, there is absolutely no correlation at all. And this standardization is pretty common in the statistical uh, uh, um, academic or epistemology. Um, maybe I decoded them to maybe give them 20 per increments. Maybe in some books they actually put them, they have divided them into three or four categories, but I think this is a better explanation of the metrics and the breakdown of the metrics and how they should be interpreted. So since in our case we have a coefficient of 0.46, this means that it falls here, and it says that it's a weak positive correlation. And since it's very close to 50, we can say um, it's almost close to medium positive correlation. It's not too bad. Um, it's like midway. So that means there is a almost moderately positive correlation between earnings and education years. That means and then so since we have established that there is correlationship and it is almost medium or moderate positive relation correlation, then let's go and check if this is also statistically significant. So we run a correlation t test, a correlation test. So for the correlationship, pretty much use the function COR and first variable, second variable, and if you're going to have missing data on your data set, use this fraction here, use complete observation. Otherwise, you're going to get an A result because of missing values on your data set. And always, if you don't use the method, then if you don't add the method, then by default R will select Pearson's correlationship. But I would just add in there Pearson just to be safe. So this is the code to run a correlationship. And for the core test, pretty much core.test, this will test the correlationship, the first variable x and the second variable y, and then also make sure to use this part of the function so that it can outlaw or disregard the missing values. So let's go check this relationship, statistical significance, since we established that it's a moderately positive relation. And as you can see, that the p-value actually falls below 0.05. It actually falls way below 0.01. So this means that the correlationship uh, is not equal to zero. That means there is a statistically significant correlation between these two. However, it's moderately positive. It's not strong. It's halfway, but it is statistically significant. So that was for our first relationship correlation relationship test. Correlations test. The second one is between the family size and savings. So let's test if there is any relationship between the size of a family and their savings. So let's say if a family size is bigger, do they have more savings, or if they're smaller, the family size smaller, do they have less saving? Let's find out. Like I said, we don't have to do I've already done the normality test on the background, so I don't have to do it again to save time. But to begin with, we use the plot um, function to plot to look at the scatter plot of both of the variables to see if we can visually detect any correlationship, which we do. In this case, this looks very similar to the chart above, except that it's the reverse. In other words, it's negatively correlated. In other words, when one variable goes down, the other variable goes high. Or when so so once we plot that, we're going to go ahead and check the correlationship coefficient test. And again, for that, since this is the normality assumption has been verified and it's a normal data set, distribution is normal in the data set, so we're going to go ahead and use the Pearson correlationship and always make sure to use complete the observation if you have missing values, and the method by default is Pearson, and if you don't put it, it will always use Pearson's test. So bingo, this is a 0.783. And not only that it's high, it's also a negative correlation, as we just saw it. It means when the savings go high, that means when the family size goes down, meaning when the less the number of family, the more likely they are to have more savings. Or the more their family sizes, the less likely they are to have more savings. So if there are families that actually owe from their savings rather than having savings, but then their family who have savings, uh, you know, considering that they have less number of people in their family. So as you can see on this chart, savings goes high, family number goes down, or family number goes down, savings goes high, negatively correlated. So 0.78, let's look at our metrics. This is the this is for the negative correlations. Sorry, I made a typo here. Negative correlation. And so each of these variables is supposed to be, each of these numbers is supposed to be negative. So I apologize for that. So since this is a 0.70, this is going to be a highly strong or high strong negative correlation. That means it's a very it's a highly strong, very almost very strong negative correlation. So there's a high strong negative correlation between family size and their savings. So if a family size and it's a negative. So if a family if a fam the less people are in a family, the more they're going to have more savings. Let's check this test. Let's check this correlation. Let's test this correlation in terms of statistical analysis, statistical significance. There you go. So, of course, we're going to have a p-value that's way below 0.05 or 0.01. So that degree of freedom 98, 99 sample data minus 1 because it's a sample, not population. It's not equal to 0, and the 98, 95% confidence interval is is for the estimate. So this relationship is not only strong, uh, negatively strong, it's also statistically significant. So the third case study is the correlation between family size and education years. Now let's look at if family size and education years have any correlation. So as always, let's plot this. Oh, so now we're looking at actually no trend. There's no trend, neither positive nor negative. It is just everything is scattered around the chart, and we don't see any special trend. We don't see any we don't see any significant shape on the scattered plots or the scattered data. So let's still check the correlation, Pearson's correlation, and we see that it's minus 0.13. And as you can see, minus 0.13 falls here as negligible negative correlation. That means very, very, very weak correlation. And it's negative. So that means if there's any relationship, it's very, very weak and it's negative. So if education years goes high, the family size should go low. Let's check if this is statistically significant or not. So it's also not statistically significant. That means, as you can see, 0.17, the p-value. It's below, it's above 0.05, even above 0.10. So in terms of social science or economics, this p-value is not significant to accept a hypothesis test. So I just wanted to make sure that I also mentioned the confidence level here. If you ever wanted to add um, the confidence interval, you can and designate what what uh, what level you want to add. You can pretty much put confidence at level and then put the proportion of it. So if you want 0.9 or because a lot of most of statistical tests for anything related to sociology or social related studies are 0.95, but sometimes in science and overall in science, the standard is 0.99, but I've also seen 0.90 p-values for depending for some disciplines, depending on the nature of study. So the last thing is the the correlation matrix. So let's say, for example, we have almost 9 or 10 variables here, and you don't want to like sit down and run each variable against each other to look at their correlationship. You can actually do a metrics a metrics. In other words, you can plot all the variables in one visualization. It's too small to see, but pretty much 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 variables, and each variable are plotted against each other here on the chart. So let's say family size versus education year. So family size and education, this will be this plot. And let's say age and family size will be this will be for these two. Or let's say education years versus age. So this allows you to actually have a glan a study at a glance type of analysis where you can look at trends here and select, for example, oh, this looks like there's a trend in this one. Let me study this one. And instead of just wasting time to go and study each one of these variables against each other, which could be very time consuming. Let's say this is worth studying, or let's say this is worth studying. These are worth studying, you know. So this is a good practice, but you can either look at the right side here or left side because one each it mirror this mirrors this side. So um, just wanted to make sure. And also, you can also look at the correlationship coefficients by, uh, doing a matrix in terms of crosstab. So let's say you're looking at family size versus family size. It's one because it's testing itself against itself. Education years versus family size, we just check 0.13. Age of years, family size 0.06. So pretty much another easy way to do a correlation coefficient test at a glance. So you don't have to run them individually. Let's say another significant test that we can do could be this one, family size versus number of months worked, or maybe this one, family income versus number of experience. This is a good positive coefficient determination here. So just a good practice in order to be able to determine relationships before digging deep into individual variables to test their significance. I'm hoping I did not miss out any important thing. Um, I think that will be it for this video. Thank you for your time and have a great day or night.